Two computer programs developed from the Science and Technology series are available on disc for the BBC B Computer, together with a booklet for teachers. These can be obtained from GSN Educational Software, 214 Stamford Street, Ashton-under-Lyme, Lancashire, or from the education officer of your local ITV company.
This is one of the engines in a collection at Birmingham Railway Museum. It's one of the smaller shunting engines. Experts at Birmingham restore scrap engines, carriages and wagons and bring them back to working order. And they end up looking as good as this. But not all the engines look quite so smart. This is how they arrive, rusted, damaged, and with pieces missing. Just look what years of neglect have done. The wood of the wagon suffers as well. Most unprotected materials will eventually show signs of decay. Wood rots, iron rusts. And it's not just these old steam engines and their carriages. The window frames at home, doors, gates, the nearly new car. Without proper looking after, all will show signs of wear. Corrosion has started. It's rust that causes the most damage to engines. The paint cracks and rain gets to the steel. Eventually, there is little paint left. The corroded pipework will need to be cut out and discarded. The layer of rust and what paint still remains are ground away, down to the bare metal. And the whole of the engine is repainted, slowly and carefully. This red paint is just the first priming coat. After 18 months of engineering work and many coats of paint, an engine looks like this. This is the fourth rail bridge, completed in 1890. It's made of steel, and it's over a mile long. When it was first built, the bridge was coated with boiling oil, followed by 6 coats of paint. Until recently, those steel girders needed to be repainted about once every 4 years. 30 men worked full-time to keep the fourth bridge free from corrosion. And British Rail owns huge numbers of other structures. All are liable to corrode.
This is a typical railway footbridge built out of steel. It's very old now. It was built in about 1944. And one of the problems with old structures like this is particularly at the edges where you get dirt accumulating on surfaces, and it holds moisture against the steel, and the moisture gets underneath the edge of the paint. It starts the steel corroding, and the corrosion gradually creeps underneath the paint, pushes it off, and you can see all down these steps the corrosion is quite bad.
So what's the cure?
Well, first of all, you've obviously got to remove all the rubbish and dirt from the corner of the step there, scrape away all the dirt, and then get rid of the rust on the steel by scraping like this. And probably you'd wire brush it as well, and then applying a good coat of primer and a finishing protective paint to protect the steel against further corrosion.
At laboratories in Derby, British Rail tests different types of paint to see how well they perform. Painted test panels are left out in all weathers. But experiments in the open air can take a long time to produce useful results. This equipment speeds up the effects of corrosion. What would take years to complete on the roof now requires only a few weeks in the laboratory. Now, Frank, tell me what you've learned from these paint samples.
Well, what we're doing here is we put these paint samples in a drum and we bombard them effectively with a salty fog, which accelerates the weather outside and it causes the steel to corrode very quickly. We deliberately damage the paint panel because we need to get the moisture into the steel to get the corrosion going. If we didn't put that damage on, with a good protective paint system, it would sit in there for years and not much would happen. And you can see there are some further panels up here where the paint has already been scraped away, and you can see how the corrosion has spread underneath there. So by this means, we can put different paint systems in, we can put some in that we know the properties of out in the field, and we can compare a new system with them and see how it's going to behave.
And find the right paint for the job.
And find the right paint for the job, that's right.
A good paint will have a number of other important properties. These stripes of paint are all of a slightly different thickness. Thin at the top, thick at the bottom. A good paint of the right thickness won't sag under its own weight. A poor paint does sag. The paint coat may be too thin. Painted surfaces get hit by flying stones, the wheels on luggage trolleys, anything. Brittle paints will crack and let in moisture. Good paints bend with the metal and leave the paint surface unbroken. Gloss paint should be properly shiny. This device is measuring the light that is reflected from the paint and onto a photocell. But not everything can be painted.
The rails are made of steel that obviously the trains run on. And generally out in the open air, whilst they get wet through rain and so on, corrosion is not a great problem. But tunnels do have wet patches, and there you can get quite a severe corrosion problem, which I hope we shall see as we get into the tunnel. cold in here, isn't it?
Yeah.
Now, most tunnels for a lot of their length are dry, but we'll see a bit later on along this one, we should come to a wet patch.
Yes.
The water comes through, it drips on the rails, and because you've got no sunshine to dry it off, you've probably not got very much draft, the rails stay wet for most of the time. Right, here we are at one of the wet spots now, and you can see here that the head of the rail is quite badly corroded. You can see the rail fastenings also, the bolts are quite badly corroded, and there are some quite hefty pieces of rust that you can get off the rails quite easily with a scraper. Very often there's not a lot you can do, except obviously the rails would have to be replaced more frequently. But in special cases, we do have greases of various sorts that we can coat the rails with to keep the water out.
I see.
It's quite simple, but it's reasonably effective.
It is quite bad down there, isn't it?
Yes, it is.
In damp conditions, metals react with air to produce oxides. The most usual way to stop oxidization is to make a barrier between the air and the metal. And the most common barrier is paint. But this equipment is coating zinc with other metals, copper, nickel, and for a shiny surface, chromium. The coatings of metal are joined by electroplating. Copper is the first layer on the bare zinc. Large copper rods form the anode of the cell. Copper sulfate is the conducting electrolyte, and the zinc is the cathode. Gradually, copper ions move from the electrolyte and form a thin layer of copper on the zinc. These car parts move slowly from one plating bath to the next. Layers of metal build up on the zinc, sealing it from the air and the moisture that would cause corrosion. This bath is plating with nickel, and this is the nickel anode. The orange bath contains chromium salts, which give the shiny top coat. Car manufacturers have to deal with all the problems of corrosion. A car body is made of steel. It has the strength of steel. But uncoated, that steel would rust away. Many of these steel sheets have already been coated with a layer of zinc metal. Soon, the car body will be covered with layers of special corrosion-resisting paints. This bath puts a layer of paint on all the metal surfaces. The paint is attracted to the car electrically. It's similar to the electroplating bath. A thick plastic coating will harden to protect the car from stones thrown up by the wheels. And finally, several coats of paint are added, including this glossy top coat. All corrosion protection.